Hey class, after talking with a few of you, I thought I'd make a quick video to give you guys some pointers on doing the lab. So first I'm going to talk about part A, and then I'll also talk briefly about part C. So in part A, I asked you to do something super lame. I asked you to measure the width of just a single piece of paper, and I asked you to do it 10 times total, 5 times using one ruler or meter stick or something, and 5 times with some other measuring device like a tape measure or something. Just to be really clear, okay, now in theory, you should be able to measure your object 10 times, and you should, in theory, right, get the exact same width because it just has one set width, this piece of paper. But what's going to happen as you measure it using the methodologies I recommend, you're not going to measure it to be the same every time. And the reason is because in any experiment, anytime you're determining something experimentally, like you'll do measuring this piece of paper, there's always a certain amount of random error that results from the fact that you're doing an experiment in nature using limited tools. And so that's kind of the point of this first experiment. So what I want you to do is I want you to take your piece of paper, and on each trial, I want you to just place it on some random location on the piece of paper. Okay, or on the ruler, I mean. I don't want you to line it up specifically or perfectly at any one location. Put it at some spot, take your measurement, move it, and do it again. If you leave it, if you measure, where you're lining up perfectly with one side of the ruler, and then you're leaving it there every single trial, what's going to happen is you're going to get something known as confirmation bias. You're going to measure it and assume it's going to be the exact same as what you got the time before because you want it to be the same for consistency's sake. So make sure you're doing it differently each time. To give you a little example, I went ahead and took a picture of a piece of paper laying over my meter stick that you can see here. If I zoom in a little bit, I'm going to show you how we go about figuring out where exactly we're at to the 4th decimal place with each side of the paper. So if you looked at the data table here, you see that it's asking you what is the physical location on the meter stick of the left edge of the paper and the right edge of the paper, and then you can find the width by subtracting those two. Okay, so if we go back to our image here, the left side of my piece of paper looks like is located right here. Now let's go ahead and measure this to 4 decimal places as I mentioned. So the first decimal place would be the tens place. So if you look, I fall between the 0 and 10th centimeter mark. So my first decimal place would be just a 0. So if I'm collecting my data, let's see here. Let's pull this up. So here's just a data table I created for us. All right, so if I type this in 0.0, and then the next value, I believe, was a 4. We can go back and double check. Yep, so 0.04. And then the next one would be the millimeters, which are these tiny black lines. Since I see 5 of them, and it lies between the 5th and 6th millimeter mark, my next value would be a 5. And then my 4th decimal place, the last one, would be an estimated digit. Okay, so estimated on a scale of 1 to 10, how close is this to the 6th millimeter mark? So if you look, you can almost start to see the 6th one. So it's right at the edge. So I'm going to estimate my final decimal place to be a 9. All right. Then you would continue on and do the same thing with the opposite side of the piece of paper. So you come over here. So we lie between the 26th and 27th centimeter mark. So my first 2 decimal places would be 0.26. If you notice, I see the 5th millimeter mark, so the next one would be a 4, since only 4 are covered. So let's just see 0.264, and then we estimate on a scale of 1 to 10. Again, it looks pretty close to the edge, but there's a little more space there, so maybe I would estimate something like a 7. So we go back here, and then we would put 0.2647, and then our width of our piece of paper is just equal to the larger one minus the smaller one, and that would be my width. Although, if I notice just looking at this, I made a mistake in my table. I did not put units, so make sure you include units for all of your values. So anyway, that's how you're going to do that. Just make sure you understand what's going on for measuring. Now I want to talk briefly about part C. Part B is usually pretty straightforward for people. So I want to move forward and talk about part C. So in part C, you're going to be using the tracker video software, looking at an object being dropped, right? So if we fast forward here, Okay, so here I tell you there's a video that I made showing you how to use it, and you'll get to see it again here in just a second. But you're going to be looking at an object that's experiencing some constant acceleration. I went ahead and picked just a toy of my dog Gus, a little squirrel thing, chipmunk maybe, that I dropped. All right, so let's go ahead and look at that. All right, so here's my video. You can see of me dropping it. And what I'm going to do is I'm going to track and try to get position as a function of time data, as well as velocity as a function of time data. Now it's a little hard to see, so I'm going to zoom in a little bit here. All right, and I'm going to track, go back to when it's up in my hand, I'm going to create a new point mass. Track a new point mass, track a new point mass. It automatically jumps to the very beginning of my video, so I have to fast forward my hesitation before I dropped it. All right, so now I'm at the beginning. I'm going to try to track the chipmunk's belly. So I'm holding shift and I'm going to click on the very center of the chipmunk. And the cool thing is the program automatically advances to the next frame each time I click. So I'm just going to keep clicking the belly of the chipmunk here as it falls. It rotated a little bit, which is a bummer, but that's okay. Now you notice it's getting pretty blurry here, right? It's like, oh boy howdy. But just go ahead and continue to try to do your best to approximate where its center is in each frame. Yeah, see, mine's really blurry, and you can reduce the blur by choosing a like a slow motion setting on your camera or something. But I'm just going to continue to click here until we get pretty much to the ground. Once it hits the ground, then you're kind of done. There's an outside influence. So I'll stop there. Over here I see I have my data. Oh, but I noticed, wait, these numbers are crazy, 400 and so on. I never calibrated my video. Oh, I almost forgot. So if I go back, I need to do a new calibration. So to do that, I come over here, drop down menu, click New, Calibration Stick, and it generates a new calibration stick for me. All right, so I have my calibration stick here that I'm trying to create. I did pause the video there for a second because I clicked on something incorrectly. But if I want to do calibration stick A, if I hold shift, I'll click on one end to start it, and then click shift on the opposite end to create the calibration stick. And now if I want to zoom back in, zoom in up here. This is from when I messed up earlier, so I'll just get rid of that. But yeah, so we set this up. The length of my ruler is 30 centimeters. So instead of 300 meters, that should be 0.30 meters. So that should set our calibration for what's going on. I also went up here and clicked on my axes to create an axis for us as well, setting the bottom, and maybe I should adjust, setting the bottom at ground level. So if you look over here, we can see when my time starts counting, I have my initial height of about 1.5 meters off the ground, and then as I click down, it moves down, getting closer and closer to 0. Now I can come over here and click on my table. Maybe I'll move my picture of me so you can see it better. I click on the table, and I can choose what values I want. If you notice, my X stays right around 0 the entire time. That's because it's not moving in the X direction, it's only moving vertically. So I can go ahead and get rid of X because I don't care about it. I want my Y, and I also want my velocity in the Y direction. All right, so now I can go over here, highlight my data that I'm interested in, and then I can go and paste it. Let's see, Control C, and paste it into my spreadsheet here. Control V, and there it is. So now from here, we can use this information, and you can change these numbers to a different format if you want, just into a plain number or however you want to represent it. But now you can go ahead and create the plots that you're interested in. So you can take your time and position and do a scatter plot. So again, we'll come over here and create a chart. Maybe insert chart. And then the default is a line chart, but we want a scatter plot. So I'll go down here and click scatter plot. And then you see that you kind of have this quadratic type form. And I tell you, you need to do a fit. A quadratic fit, if you look at the lab, it talks about doing a quadratic fit in the form y equals at squared plus bt plus c. So I want to go back and do that. And so I go to customize. Oops. I need to really move my picture. Let's see. Somewhere in here, under customize, we have the ability to create a trend line. It's under series, so you click on series. Here's your trend line. Now the default is linear trend line, which is what you're going to want when you do velocity. But now that we're doing position, we want a polynomial of order 2, time squared. So there's our polynomial of order 2, and we want to look at the equation. And so here's our equation that we could enter and use for collecting our data. So it's a t squared, but instead of t, it's calling it x. So a would be negative 3.37, b would be 7.27, and c would be negative 2.32. All right, now notice this negative, and the fact that these two values are not what they should be is because I didn't drop the squirrel until 1 second after my wife started the video. So that delay that I had kind of threw those values off a little bit. But that's how you're going to do that part. And then, oops, for the next portion, you would do the same thing, but instead use your time values and your velocity values. And if you notice, we don't have the first velocity value, so we'd have to start a little bit lower. Down, just start down by 1 second. But then you drag down, highlight your times, and highlight the velocities, and then you'd go through the same format of creating a scatter chart and then doing a linear fit this time. So hopefully that helps you guys out just a little bit. One thing I'm noticing even as I just look at this here, if you notice, I started before it's actually dropped and I ended a little bit too late on here. So you might want to actually cut off the very first 1 or 2 trials before it actually started moving, just so you know. But anyway, here's my linear equation. So you'd have A and B once again. All right, well, I think that should kind of help you all get started. Let me know if you have any questions, and make sure that you pay close attention to what these A, B, and C values mean. Because if you look at our quadratic equation over here, for example, it looks pretty similar to our equation of motion that says y final equals y initial plus v initial, y times time plus 1/2 acceleration times time squared. Make sure you make those comparisons when working on your final lab write-up. All right, let me know if you have any questions.